Okay, good. Yeah, thank you, Matthew. So yeah, this is about this library Jacoby, and yeah, here are some links that you can check when you look at this offline. So this library is about error propagation, or specifically about that prerequisite that you need for error propagation, namely to compute derivatives. So when you do error propagation, you have in the 1D case some function f of x that computes your y, and then you compute the errors. You need your error on the x and the derivative of your f, and then this gives you the uncertainty in the y. I mean, this you can find in textbooks. And when you have 2D or actually n dimensions, then it looks a little bit different. Now you have a vectorized value that you map to another vectorized, another vector. And when you do the error propagation, you have the covariance matrix in X and this Jacobian 2 times, and this gives you then the covariance matrix in Y. And the Jacobian is just the derivatives of all the Y values by all the X values. So this is how error propagation works. And now how can you compute these first derivatives? I mean, you can do it by hand when the situation is simple. But this is, of course, error-prone and tedious, and you probably don't want to do this by hand. Then you can use a computer algebra system, for example, SymPy, I like a lot, or use MATLAB or whatever, or Wolfram Alpha, so this also works. On the other hand, this is still a little bit tedious. I mean, you have to write your formula then in some kind of language that this computer algebra system understands. Then you can use, if you don't want to do this, you will have another option that's automatic differentiation, called AD for short, because I will refer to this several times. So this is what TensorFlow does, or JAX, or numdiff tools has this implemented, or what also the popular uncertainties library uses internally. The problem with this, I mean, okay. So this is almost, almost you just put in your normal, you just write your normal Python functions and it gives you derivatives, and this is almost very easy. But there's still some caveats with this. So then the most flexible and general thing is numerical differentiation. That's the approach that Jacoby uses, and numdiff tools also does this. So Jacoby is cool because it implements, as far as I know, it's the only library that implements this derivist algorithm that was originally developed by John Derrico in MATLAB. And he has found a nice algorithm that's very robust and fast. So what he does is, in a nutshell, so he computes a very simple derivative like this one here. This is the forward derivative, but you can also use the backward or the central derivative for a given step size h. And normally you want to make this h very small so that you get this error here very small. I mean, this is computing the derivative by a finite difference. So, but he doesn't do that. So he starts with rather large h, and then he reduces the h. So for example, it takes half of it or something, and then repeats this several times. And then you get several values for your estimate here at different values of h. And then you can fit a polynomial to these value pairs, and you can then use the polynomial to extrapolate to the value where h is 0. So this should give you in principle the infinite, I mean the perfect derivative. And the nice thing is, because you use a polynomial here, you can do some error estimation as well. So basically you just treat the numbers that the computer gives you as random numbers, and this allows you to compute some error on your estimate. And then you can stop actually when the error is good enough, and you can stop more early than other approaches. So I compared Jacoby to numdiff tools. So when you set it up to have the same quality, the same precision as numdiff tools, it's actually much faster, because it exploits vectorized computations better than numdiff tools does. So what you see here is 4 different functions where I computed derivatives for, so x squared, exponential. This is just a mapping of any vector to ones, and here it's it's like a chi-squared, no? And you see the time that numdiff tools used here in orange, and in blue is Jacoby, and this dotted line is the ratio. So I mean, the fact that this loses less time is good, and this is the factor that you save, so it's significant. Especially here for this case, it's very dramatic, where you have 1,000 times faster. Where it's not so, where you don't get so much benefit, but still live it, is when you have a function that maps a large vector to just a number. There, Jacobi cannot really accelerate as much more. Okay, and now that you have these cool derivatives, you can do error propagation, and there's already a function in Jacobi which does this. So you write your Python function like this. X can be a vector here. This is your X values. This is the covariance in X, and then you just say propagate, and then you get your Y values and the covariance matrix in Y, and you can check that this is correct. So recently added was something that we actually often use. So, I mean, originally, this is already the general case. You can cover all the cases here, but it's a little bit tedious when you have just two variables or three or whatever, and they're all independent, and you don't want to write down this covariance matrix here. So there's a new feature added that for very simple functions, which depend on arguments that are mutually independent, you can also just propagate like this, where you pass the numbers and the errors, error squared, and then it will do the right thing. Okay, this brings me already to the summary. So yeah, I implemented its numerical differentiation algorithm of John Derrico in this library here, and it's really cool because you can compute the derivative now for any Python function that is at all differentiable. It doesn't matter what this Python function does. It can call into number, it can call into C++, it can do whatever it wants. This always works, and that's not true for AD libraries, which only work when you stay within that library. So you cannot mix TensorFlow with number, for example. That's not straightforwardly, and you still get your derivatives. And it's also not intrusive. So especially what I don't like about uncertainties is that you have to use their special arrays and their special numbers. Otherwise, this doesn't work. So you have to change the whole code when you want to start error propagating to follow this library. By Jacobi, you just have one small place in your code where you use this, and otherwise it's completely, it doesn't matter what your code does elsewhere. So the caveat is that this is not as fast as these other solutions, but usually it's fast enough actually, and it's faster than non-diff tools, and it's numerically super robust. So, this is really, I have to stress this, when you look at other algorithms for computing derivatives, they're not as robust as this one. And that's, I think, very important. You don't want to have wrong results. Okay, very good. So, that's what you can do right now. You can do propagation, and as an outlook, I also want to apply this algorithm to compute the Hessian matrix for some function. Basically, then you can replace the minute algorithm with something that's maybe more robust. Okay, that's all. Thanks.
Nice. That was quite impressive for a short period of time. Okay, thanks very much for that talk. We have time for questions, so let's go to Slido. Okay, so we have one. So why care about precise derivatives when we anyway assume that the function is linear within the uncertainty interval? For example, why not have the plus and minus 1 sigma interval?
Yeah, right. But when you make a library, you don't know what the uncertainties are, what are driving your uncertainties. So in principle, you're right. You could stop when the error of this derivative is small compared to this non-linearity. But to know in general how non-linear your function is, you already need the second derivative. So you kind of run in a circle there. So this approach is just do this linear derivative as best as possible, and then yeah, that's at least the best you can do from that point of view without knowing more about your function.
Nice. So since I don't see another question on Slido right away, I'll take some chair privileges to ask one of my own. I know you, and I know that you write some really nice, cool libraries for analysis in general. So do you have kind of a pet use case that you haven't shown us yet for where using Jacobi with Numba has proven to give you some really nice speedups?
So I use this all the time. So, and I also tell my students to use this because, yeah, I think it's very easy to use and very simple and works very well. So, and yeah, you can also do this for really complex stuff. So, for example, when you do fit in your function, normally you don't think of a fit as a derivative or a derivable or smooth function, but in fact it is. And you can even use this and propagate errors through a fit with this.
Okay. So, and I think that there's one more question that kind of came in, but I think you somewhat answered it, which was, can Jacobi be accelerated with numba, assuming the function to differentiate works with numba? But you've said that that works.
Yeah, definitely.
Yeah.
Works with anything. It can be any Python function.
Okay. Yeah, that's quite powerful. Okay, so unless there's any other questions, let's thank Hans again.